Hello, everyone. My name is Andrew.
And my name's Chris.
Hi, I'm Johnny.
I'm Collie.
I'm Nico.
I'm Shireen,
I'm Simon.
and this is our senior design project. So a little bit of overview about how this presentation is going to go. We're going to start with an introduction, and then we'll get into a system overview of our entire interdisciplinary project. We'll then dive a little deeper into the subsystems, specifically the mechanical and the computer engineering components, and then we'll sum it up with a few conclusion statements. So starting with the introduction. First off, why automation in the agricultural industry? The increase in human population has introduced a labor shortage in the agricultural industry. And in order to keep up with the demand for food and keep overall food production as sanitary as possible, the industry has been slowly automating bulk food processing tasks. Food safety is also of the utmost importance, especially in light of recent events, where the risk of human contamination needs to be reduced as much as possible. This opens opportunities for research and development of possible technologies that could be used for food processing automation. As our team did our review and research of the current industry, we found that automation already exists in the forms of different elements of intelligent robotics, such as automated tractors or robots that do berry picking. There are 7 automated processes already existing in the food processing industry, as listed below. But our team found that there was not much development in technologies specific to handling delicate foods, such as basil leaves or other types of seasoning.
Based in Modesto, California, Stanislaus Food Products is partnered with us for our senior design project. They're a tomato growing and processing company, meaning they see the tomatoes in the field through to the canning process of a final tomato-based product. In this process, however, the company told us that the two tasks need to be automated. The removal of basil leaves from branches and the placement of these basil leaves into cans. Our project scope focuses on the latter, hoping to place 1 to 2 leaves in cans each second, as specified by the company. In combination with the speed, we hope to not damage or blemish the leaves for aesthetic purposes.
The goal of this project is to achieve proof of concept of a system capable of picking and placing basil leaf by combining robotics and machine learning. This means we need to develop a machine learning model as well suited for this particular implementation to recognize and classify leaves. Prototyping a robot that can move a gripper quickly and accurately and pick up a leaf. After discussing with our client, we came up with 4 requirements that help guide us through the development. These requirements are ideal goals that we got from our client. The can conveyor travels around 1 to 2 cans per second, so our cycle time of the system should be around 1.5 seconds ideally. The speed of the robotic arm is also based on this time. We want a good leaf recognition accuracy to reduce food waste and the cost for our client. The leaf quality accuracy is required to ensure good food safety, and these are the ideal requirements that we are striving for.
Concept of operations. Our hope is that our robot can be easily implemented into Stanislaus Food Products' existing assembly line. As of now, workers have buckets of leaves which they'll manually place into cans moving by a conveyor belt. Our robot would be implemented with an additional conveyor belt parallel to the existing conveyor. This second conveyor would have basil leaves on them such that our robot can have a continuous supply of basil leaves to place into cans. So we'll now bring you through a system overview of our basil leaf robot. On screen, you'll see the final design of our basil leaf robot in SolidWorks. We can note the parallel conveyor belts which will be carrying the basil leaves and cans. These leaves and cans are positioned under a lighting box to provide consistent lighting for the cameras. As shown in the GIF on the right, the part that appears to be drifting away from the structure is the position manipulator in charge of moving the leaves into the cans. We'll delve more in detail of the components later in the presentation.
There are 2 main systems. The top part is a vision system with a Jetson, and the bottom is a mechanical manipulation system with a Raspberry. The vision system is originating with 3 cameras attached to it, with 1 looking on the basil leaf conveyor belt, 1 on the can conveyor belt, and the last one as a final redundancy check for the gripper. The redundancy check is to ensure that when the gripper thinks it picks up a leaf, the camera checks it actually did pick up a leaf. However, throughout testing, we realized that we could perform the redundancy check using the gripper itself by measuring the change in suction pressure without the need of an additional camera. The mechanical manipulation system is in charge of controlling the motors, the vacuum, and the linear actuator of the gripper. We have an additional limiter that prevents the system from overshooting the physical system itself.
All right, so now that we've talked about our component diagram, I want to walk through our software process model. So the top shows a process for moving the suction gripper, which is controlled by a Raspberry Pi board, whereas the two bottom areas are focused on the vision system and are controlled by an NVIDIA Jetson board. Initially, these two boards communicated over serial, but due to COVID, these systems are now separate and operate independently. The software process was designed to run using a client-server relationship where the Raspberry Pi or the movement section of the system would query the Jetson board for information on both leaf position and drop times. So as you can see here, the general idea was that the Jetson board would be constantly waiting for requests from the Raspberry Pi. So it would be identifying leaves and creating a list of coordinates where those leaves could be found, as well as for the can tracking the movement of each can and calculating the correct time to drop. Up top, on the Raspberry Pi side, it would query for coordinates when it needed new coordinates. It would receive those, move the arm to those coordinates, pick up the leaf, and then check to make sure the leaf had actually been picked up. If it had, it goes to a predetermined drop zone, where this time it would query for a drop time. So it would send a signal to the Jetson board, and when the Jetson determined that there was indeed a can underneath it, it would send a signal back saying to drop the leaf now. The leaf would be dropped, and the whole process would be started over.
Our robot consists of 4 subsystems. In a general sense, position manipulation of the leaf is achieved by stepper motors and linear actuator. Attached to the Z-axis of the position manipulator is the suction gripper in charge of picking up and dropping leaves. The frame essentially assembles the other subsystems and provides consistent lighting for the vision processing. The vision processing being the identification of the leaves and cans. I'll hand it off to Andrew, who will walk you through the first subsystem.
So the first subsystem tonight is the frame. The frame subsystem is a platform on which other subsystems fulfill their goals. This frame supports the position manipulation subsystem and the vision processing cameras that look at the basil leaf and tomato sauce cans. Because the aluminum extrusion used in the position manipulation is a bit heavy, the movement of the position manipulator can cause the frame to move if the frame is not bolted down. So it's important for the frame to be able to withstand the vibrations from the movement. Furthermore, the frame serves as a master coordinate system for easy communication between the subsystems. The origin of this master coordinate system is the corner of the frame marked in red. Some design features we included is a synchronized operating plane between the top of the tomato sauce cans and the basil leaf conveyor belt. This minimizes the up and down movement required of the position manipulator. Furthermore, different heights for the cameras are constructed into the frame to allow for the optimal field of view. The frame itself is designed to be made out of extruded aluminum for structural integrity and manufacturability. The final design also calls for Delrin plastic sheets to provide controlled lighting for the cameras by blocking external lighting from casting shadows. The insides of the Delrin walls have LEDs with a diffuser to provide controlled lighting. Delrin is also FDA, NSF, and USDA certified, making it the plastic of choice in food handling applications. The current status of the prototype is exactly the same as the design, except for the Delrin walls. In the prototyping stage, we used MDF because it is lightweight and easy to handle. The position manipulator and frame are in 2 separate locations and were unable to be integrated. LED lights also line the inner MDF walls to provide the consistent lighting. The testing done on the frame subsystem is mainly to make sure that the build satisfies the requirements of this vision processing subsystem. This includes providing consistent lighting for the video capture of the leaves and a reliable master coordinate system that can translate pixel space to physical space. The picture on the right is a test with 6 sample leaves from one of my trees and their locations in relation to the master origin shown earlier. From the location of the camera and its field of view, we are able to find the exact locations of the corners of the picture and extrapolate the exact location of the leaves from the pixel space.
Thank you, Andrew. And the next subsystem, the second subsystem to discuss, would be the position manipulator. So this system allows us to get from point A to point B. And it does that by giving us 3-dimensional navigation. There's about 2 by 2 feet of area of navigational space in the X and Y directions, and about 2 inches in the Z direction. So this manipulator is 3-axial with 3 motors. All movement is controlled with the Raspberry Pi, and communication is done with the vision board in order to receive positional coordinates. Additionally, the movement should be repeatable. It should be able to go anywhere accurately and quickly. So here shown is the current SOLIDWORKS configuration. Going through each stage of movement, we have the X stage, which is a belt-driven stepper motor. It's connected to the Y stage T-slot by both at the front and the back, and this whole stage slides along linear bearings. The Y stage is rack and pinion driven, also a stepper motor. It moves a piece of T-slot that is mounted on a parallel piece and also using linear bearings like the X stage. The Z stage is a linear servo, and this is mounted to the end of the Y stage, moves between an on and off position controlled through pulse width modulation, both to touch the conveyor or the Basil leaves, or to retract and go to the can. And all movement is limited and calibrated with limit switches on each corner. And this design is similar to a gantry style robot. One of the big differences is the actual movement of the robot is directed outside of the frame, and all this allows the gripper to move. So this is the physical build of the structure, which was completed during spring quarter. And this design was used to provide us with our performance data, given speed, repeatability, and gripper data. And one other thing to note is there's the 3D printed mount for the Y stage rack and pinion, and everything on the Y stage is horizontally mounted in order to provide less vibration from the steppers and to keep us more stable. And here is the table that has our actual performance data from the spring quarter testing. It gives the speeds of each stage of the robot in inches per second, an accuracy drift measurement, which shows us positional accuracy repeatability data, and also on the last column is the total cycle time, which ended up at being around 12 seconds, which includes the entire process from movement to the Basil leaf to placement into the can to movement to the next Basil leaf.
Thank you, Johnny. Next, we will be examining the suction gripper subsystem. The goal for this subsystem was to provide suction force and stability to pick up and drop leaves. To attain this goal, we used 3D prints for our prototyping process and verified performance through tests and CFD analysis, which I will explore in the coming slides. This subsystem is identified by the key components shown in the assembly. The suction force is provided by a low-power vacuum pump. This pump is controlled by a MOSFET transistor through the Raspberry Pi, creating a digital switch. In addition, running from the pump is plastic tubing that connects to the nozzle. Our group was able to assemble a prototype based on our iterative design process. Focusing now on the 3D printing, we custom designed 2 parts for this subsystem, a bracket for mountability and a gripper to assist in leaf control. The bracket's design supports the nozzle while providing space for the tubing to pass through. It also creates a simple screw connection to the linear actuator. Connecting these 2 3D printed components are strings and tension that provide support and balance for the nozzle. We additionally implemented a spring between the bracket and nozzle. This allows the bracket to serve as a spring-loaded platform, which provides energy absorption after hitting the conveyor belt, further prevents potential misalignment or damage to the subsystem, and stay true to the coordinate system described in the previous sections. When designing the nozzle, the main features that were taken into account were suctionability, vacuum seal, and minimal leaf damage. The main trade-off was between a multi-hole radial pattern and a single-hole design. In general, for vacuum to be achieved, there needs to be a seal between the gripper and leaf. The cross-sectional area was calculated to ensure there would be sufficient holding force in perfect situations. However, because we were working with leaves of inconsistent shape and size, we expected different performance results. The nozzle's purpose was to mitigate these discrepancies. From initial testing, we found the suction hole size itself could not be too large, as it would bring damage to the leaves. This brought us to the redesign process and implementation of the multi-hole design. The various gripper iterations were 3D printed out of PLA for this purpose. However, TPA or silicon would be other interesting materials to work with based on their flexibility. And overall, we'll see that the single hole proved better functionally in simulations and testing. A variety of simulations were run throughout the year to quantitatively observe theoretical velocities and pressures and qualitatively better understand flow. SolidWorks flow simulation was the tool used to accomplish these basic goals. Some assumptions used included the environmental pressure at 14.7 psi, the vacuum volumetric flow rate, which based on the spec sheet is 12.2 inches cubed per second, the tubing, which was modeled at 6 feet with one 90-degree mitered bend based on the real prototype, and a simulated leaf placed 1.3 inches from the gripper. The comparison I wanted to view is the velocity distribution throughout each design. The key distinction between the two are velocities at each opening, which are 390 inches per second for the multi-hull and 580 inches per second for the single hull. Although there are 25 smaller openings for the multi-hull design, this resulted in significantly less total flow if not all holes were covered. These results primarily confirmed expected results, but it was also interesting to look at the flow patterns and pressure distributions. And we'll see that physical testing served best for this performance analysis.
And speaking of physical testing, here are some of the results from the actual physical testing of the one-hole design. And this is the gripper design that seemed to have the best success rate at picking up the leaves. In the table, you can see the value of 94% of success rate. This data was collected from 150 trials using 3 different fresh leaves. And it was noted that the gripper would pick up the leaf successfully 94% of the time. When trials were ran and the leaf was not picked up, it was noted that there were some discrepancies in the XYZ position, and the nozzle was usually off center when those discrepancies occurred. Next would be the observation of drop time after the pump shut off. So other tests were run in order to see how long the leaf would stay on the gripper after the pump was turned off, and we called this parameter drop time. The release times on this parameter varied from about 3 to 5 seconds, depending on the weight of the leaf. And this is a further area to look at performance-wise in order to mitigate this problem, because it takes up a lot of our cycle time, and we plan on adding a pressure release valve if work continued on this project in the future in order to cut down this parameter completely. And on the next slide, we have, this is a demonstration that was filmed this spring, and it shows the tests that I ran on the robot in order to demonstrate functionality of the pick and place operation from going to the coordinates of the leaf to placing into a pseudo can and going to the next leaf and doing the same operation. In summary, it can be seen that there's about a 12-second cycle time with exceptional positional accuracy, as well as the weak link being the drop time at around 5 seconds.
Thank you, Johnny. Now we can talk about the vision processing system. The vision processing system consists of 2 main programs, can tracking program and leaf identification program. The objective of the can tracking program is to look at the can conveyor belt to track the can and notify the gripper when to drop the Basil leaf. The leaf identification program uses a machine learning model to locate all the Basil leaves on the conveyor belt. It will provide the gripper with the location of a leaf when asked. Both programs use OpenCV libraries for inputting and pre-processing the images. OpenCV is a library with functions mainly aimed at real-time computer vision. We use Python as a main programming language since there are more available machine learning and image processing libraries to reduce development time and complexity. On the right of the image, you can see that there's a pre-recorded demo of this software during our testing phase. you can see that there are things on the conveyor belt are circle papers instead of cans, because this was done during our testing phase. Since cans are circles anyway, we use circular paper as a representation of the can. We did do a test on actual cans from Stanislaus later on, and it worked equally well with these circle papers. We didn't take a video because it was done right before the pandemic and we didn't have time to do an actual recording of it. Behind the image, you can see that there is a bunch of numbers scrolling up and down. Those numbers are the location of the circle that is closest to our drop zone, which is the left side of the image frame.
Thank you, Simon. The second part of our vision processing system is leaf identification. Originally, what we want to do is to have leaves come down a conveyor belt, our camera identify where those leaves are, collect the coordinates of where those leaves locations are, and then send them over to a machine learning model in order to figure out which leaves are good to be placed into the conveyor belts and the cans there, and which ones are bad, which ones can be discarded. Originally, we got this working with a live video feed and the conveyor belt moving along, and we were able to use OpenCV and Python libraries to get this process running. However, due to COVID-19, we had to transition to an online dataset because our conveyor belt and our camera, as well as the mechanical system, all went distributed. They're all in different places. So we were able to do the same process with static images and get very similar, if not better, results.
All right, so as Shireen mentioned, the goal of the vision system was to use edge detection to basically find leaves. And so here I want to take you kind of inside how that's actually done. So from the start, it takes the original file image from the data set, pulls that in, turns that to grayscale, and then does a blur effect on the image. And then from there, it uses a canny filter, which is an algorithm that pulls out the important lines in an image. And so as you can see there, it pulls out the leaf actually quite well. Next, we apply a dilation to it, which simply increases the thickness of the lines that surround the leaf. And then from there, that image can be passed to an OpenCV function, which can then find a bounding box of the identified object, in this case, the leaf. And then from that bounding box, we can then find the center. So you can see there, the center is that blue dot in that final image. And that is the coordinate that is then passed on to the gripper system to identify where to go to pick up the leaf. So next here is kind of a quick demo of this actually running. So this was done on Google Colab, Google's cloud Python environment. So a couple things to notice here is the very high success rate. So it actually does very, very well at pulling out the leaves in each image, up to 99% accurate, with some only maybe getting part of the leaf, as I think one of these images may show. The center point still is identified on the leaf, but it was just off slightly. But in general, very, very high success rate. And also the speed of computation is very fast. So this is not something that is a real bottleneck of any kind in the computation. So next I want to talk about the machine learning. So this was the secondary part of our vision system. The goal here was to determine which leaves we see as good and which are seen as bad. So this may be leaves with holes in them or leaves with spots on them that we don't want to be putting in the cans of tomato sauce. So for this, we tested many different machine learning models, and we split the data up into 80% for training and 20% for testing, as is standard when running machine learning algorithms like this. So we basically fed pixel data to a number of different machine learning algorithms, and you can see our results here. So we have linear discriminant analysis up top there, and then quadratic discriminant analysis, logistic regression, k-nearest neighbors, support vector machine, and a convolutional neural network. So although we tried many different complexities of algorithms here, it actually turned out that the simplest of LDA was our highest at a maximum of around 88% accuracy. Some, like QDA and logistic regression, had a training of 1.0, but then performed terribly on testing. So this is kind of due to overfitting that training data. So LDA provided the best results for our testing data, which is what we're really looking for there. The other thing that can be noted is that although 88%, we would definitely want that to be higher, but we're definitely dealing with a limited amount of data here. So our data set that we used was about 150 images. So given a larger data set, we would hope that we could really improve this number. All right, so now we're going to jump into the conclusion. So now that we've covered all of our project subsystems, we want to talk about some of the important results and takeaways from our project. So as far as system integration and testing, we definitely initially planned to bring all these parts together. And this ideally would have been the part where we talk about the system as a whole being integrated and working on all cylinders. But due to COVID forcing us to work remotely with team members across 3 time zones spanning a total of 9 hours, this was kind of unrealistic. So despite all this, we made significant strides in each of the component parts of the subsystem, and that's kind of what we're going to cover right here.
Yeah, so to wrap this presentation up, we're going to revisit the requirements we defined at the beginning. And just a reminder, these ideal values were based on perfect performance from the client, but we see significant steps toward our goals. Cycle time was the farthest from our ideal time, specifically due to the drop time that Johnny mentioned, but also the implementation of a pressure valve could decrease this number. Speed was also limited by the motor selection, but we also wanted to explore potential use to use our system in parallel with others to improve this. Leaf recognition would be the most successful at 99% accuracy based on this online data set. And the lead quality determination overall was also close to the ideal value and could further be improved.
Some of the future work for the Basil leaf robot includes a full system integration of the subsystems we showed earlier. After integration, the plan is to extensively test the robot in real time with a wider variety of leaves. With this testing, additional tuning and possible reiterations of select parts and subsystems may be needed. We also plan to collect additional data for further training of the machine learning algorithm to perform better with a wider variety of leaves. Lastly, we plan to conduct a final round of testing at Stanislaus Food Products and to show them our complete system.
So one important thing that we really wanted to highlight right before the end was that we are not looking to replace human workers already in the field. During our research, our team found that there was actually a labor void where workers were doing monotonous, routine work that was not really utilizing the full extent of human power and intelligence. And so we looked to fill that gap in by providing an automated system that would decrease the footprint, increase food production, and decrease human contact with food. That way, while our robot is actually on the conveyor line working to categorize and move these basil leaves around, the existing labor workers already in the field could be freed up to do more intense and more involved intelligent work. So some of the final takeaways from our entire project, our team met several goals in an emerging sector of robotics that really not most of us had experience with beforehand. We did get a proof of concept and a working prototype done and still made a lot of progress and verified a lot of our results, even during the COVID situation with the distributed system. We tackled and overcame unforeseen circumstances, even as simple as communication across 3 different time zones for one project that's broken into 4 different subsystems. We established the groundwork for future development, and it's really exciting to see where people will take the basis of this project in future years. Some final acknowledgements. We really like to thank Stanislaus Food Products, specifically Chris, Dr. Kitts, Dr. Marks, and Dr. Riccomini for their continuous support and their mentorship throughout this entire process. We'd like to thank the Robotics Systems Lab, the Maker Lab, and more specifically, the School of Engineering in general for putting this entire program together so that we would be able to get this experience before we graduate. And as you all enjoy this picture of us visiting Stanislaus, are there any final questions? Thank you.